Dear students, myself Kiran MP. I am working as assistant professor in the Department of Computer Science and Engineering in Government Engineering College, Kushalnagar. I welcome all of you for this session on function composition. Let us have a look at agenda of this session. At first, we have a discussion about one more type of function known as one-to-one correspondence or simply correspondence. Once you become familiar with one-to-one correspondence, then we will have a look at an identity function. Later, we will discuss about equal function. I mean, suppose you are given two functions from the same domain to the same code domain. So, how we can identify, how we can determine whether those two given functions are equal or not. I mean, those two functions are one and the same or not. At last, we'll have a discussion about composite function. I mean to say, you'll be given two functions, and we'll see here how we can combine those two functions to form a new function. Now, coming to one-to-one correspondence. Now, in previous session, we had a discussion about two types of functions. They are one-to-one function and onto function. What actually one-to-one function? A function f from A to B. I repeat, a function f from A to B is said to be one-to-one if the elements of code domain appears at most once as an image. Is it? So I mean a function f from A to B is said to be one-to-one if the elements of code domain appears at most once as an image. Is it? Also, we had a discussion about onto function. So what is onto function? A function f from A to B is said to be onto if all the elements of code domain appears at least once as an image. I repeat, a function f from A to B is said to be onto if all the elements of code domain appears at least once as an image. Okay, so now what actually one-to-one correspondence means? It's a function from A to B which is both one-to-one and onto. I mean to say a function f from A to B which is both one-to-one. I mean the elements of code domain appears at most once as an image. Okay, and the function f from A to B should also be onto. Means all elements of code domain should appear at least once as an image. Clear? So such a function f from a to b, which is both one to one as well as onto, we call it as one to one correspondence or simply correspondence. So I think all of you are clear with one to one correspondence. So what is one to one correspondence? It's a function f from a to b, which is both one to one as well as onto. Also, one to one correspondence is referred as bijective. Now, let us have a look at an example. Okay, so as you can see on the slide, there are two sets, A with 4 elements, 1, 2, 3, 4, and B with 4 elements, W, X, Y, Z. I have given two functions, f and g. F is a function from A to B and G is a function from B to A. Okay, I repeat. F is a function from A to B. G is a function from B to A. Now, just check it whether both F and G are one to one and onto. Okay, so let me check whether F is both one to one and onto. In order to call f as 1 to 1, I repeat, in order to call f as 1 to 1, the elements of codomain B should have appeared at most once as an image. Means, if the elements of codomain B appears as an image, then it should be only once. So when I look at function f, the elements of codomain B, that is W, X, Y, and Z, appear exactly once as an image. So f is 1 to 1. So let me check whether f is onto. If I want to say f to be onto, all elements of codomain B, that is W, X, Y, and Z, should have appeared at least once as an image. So when I look at function f, the all elements of codomain B, that is W, X, Y, and Z, appear at least once as an image. So f is onto. Since f, a function from A to B, both 1 to 1 and onto, we call its 1 to 1 correspondence from A to B. Clear? So let us see whether g, a function from B to A, is also 1 to 1 correspondence. For the function g, domain is B and codomain is A. So let me analyze, okay, whether the function g from B to A is 1 to 1. So to call function g 1 to 1, all elements of its codomain, all elements of codomain, that is A, should appear at most once as an image, maximum once as an image. Or what I can say, it appears exactly once as an image. So the elements of codomain A, 1, 2, 3, 4 appeared exactly once as an image. So the function g from b to a is 1 to 1. Now let us check whether this function g from b to a is onto. To call function g from b to a onto, all elements of its code domain A should have appeared at least once as an image. So when we look at function g, all the elements of its codomain A, and elements 1, 2, 3, 4 all appeared as an image. So the function g is onto. Since function g is both 1 to 1 and onto, we call it as 1 to 1 correspondence. So now hope all of you are clear with what is 1 to 1 correspondence. Now let us know what is an identity function. See, an identity function say denoted IA from A to A. The identity function denoted IA from A to A on which all elements of A are related to itself. I repeat, all elements of A are related to itself. Then such a function we call identity function. I repeat, the function IA from A to A defined by IA of A equals to A for all A belongs to set A. It means for all elements in domain, image is itself. Okay, I mean for all the elements of domain are related to itself. Okay, as mapped to itself. Such a function we call identity function. Now let us have a discussion about when we can call two functions from the same domain to codomain or equal or not. Okay, so I mean to say you will be given two functions, say f and g. You will be given two functions, say f and g, from A to B. That is same domain to same codomain. Okay, and in order to call f and g to be equal, then for all elements small a, smaller case a, lowercase a, for all elements lowercase a that belongs to domain A, f of a should be equal to g of a. Got it? I repeat, if f and g are two functions from the same domain A to same codomain B, then we say that f and g are equal. Okay, if for all the elements say A of domain A, f of a should be equal to g of a. Then we call f and g are same or equal. Now let us have a look at example. Uh, See here, we are given two functions f and g. from real to integers. See, I repeat, we are given two functions f and g from real to integers. I mean, from same domain, real numbers, to same codomain, integers. The definition of the function f and g are as follows. See, the function f of x is defined as x. I mean to say f of x is equal to x if x is an integer. Got it? F of x equal to x if x belongs to z. That is, x is an integer. Else, f of x equals to flow function of x plus 1. Got it? So I repeat, the function f of x is defined as follows. F of x is equal to x if the input x is an integer. That is, x belongs to z. Else, f of x equals to flow function of x plus 1 if x is a real number. That is, if x belongs to r minus z. Now, g of x is defined as ceiling function of x for all x that belongs to r. I repeat, g of x equals to ceiling function of x for all x belongs to real. Now, what we observed, the observation is that f and g both are functions from the same domain R to same codomain Z. But the way f of x and g of x defined seems to be different. I repeat, the way f of x and g of x defined seems to be different. But logically they are equal. Let me justify you. So let me take one real number, say minus 3.9. Let me take one real number, say minus 3.9. Minus 3.9. Let me give this minus 3.9 as an input to function f. Since minus 3.9 is a real, okay, f of x will be evaluated as a floor function of x plus 1. So that is nothing but floor function of minus 3.9 plus 1. So what is floor function of minus 3.9? It's the greatest integer among the least integers or equivalent integer to minus 3.9. Means, now if I list all the integers lesser than or equivalent to minus 3.9, they will be minus 4, minus 5, minus 6, minus 7, so and so on. Of this, the greatest integer is minus 4. So flow function of minus 3.9 is minus 4 plus 1 is equal to minus 3. So f of minus 3.9 is minus 3. So let me give the same input minus 3.9 to the function g. So g of x is evaluated as ceiling function of x. That is ceiling function of minus 3.9. So what is ceiling function? Is the least among the greatest or equivalent integers to x. Greatest or equivalent integer to x. So when I list all integers greater than or equal to minus 3.9. Okay, the sequence are as follows: minus 3, minus 2, minus 1, 0, 1, 2, so and so on. Of this, the least integer is minus 3. So g of minus 3.9 is minus 3, which is equal to f of minus 3.9. So it concludes the function f and g are equal. So one thing I need to highlight, though the definitions of f of x and g of x seems to be different, but logically they are equal. Now let us have a look at one more example. Here f is a function defined from z to z, and g is a function defined from z to q. I mean, f is a function from integers to integers, g is a function from integers to rational number. F of x is defined as f of x equal to x. G of x is defined as g of x equals to x. So when I look at the definitions of definition of the function f and g, they seem to be one and the same. I repeat, when I look at the definition of functions f and g in example 3, the both functions f and z seems to be same. So you can't directly conclude they are logically equal. Let me justify why. I mean, you can't conclude they are logically equal even though this definition seems to be same. Let me justify. See, first of all, the codomain of the function f and function g are different. One is the codomains of function f and g. The codomains of the functions f and g are different. Okay, and if you analyze the function f, you seem to be one-to-one correspondence. I mean, the function f is both one-to-one and onto. When you analyze function g, you see it's just one-to-one but not onto. If you analyze g, it is one-to-one but not onto. So g is not one-to-one correspondence. So the functions f and g in example 3 are not equal. Clear? So what the point I need to highlight? Though the definitions of functions f and g seems to be same, logically they are not equal. Because one, the codomain is different. The other is f is one-to-one correspondence, whereas g is not one-to-one correspondence. Now, let us have a look at composite functions. See, here you will be given two functions. Say one function f from a to b, and the other function say g from b to c. One function f from a to b, the other function g from b to c. Now you can combine these two functions and you can obtain a function from a to c. You can combine these two functions f from a to b and g from b to c, and you will get a new function from a to c denoted as g dot f. Got it? So I repeat, you are given two functions f from a to b and other function g from b to c. Then you can form a composite function denoted as g dot f, which is a function from a to c. And its definition is g dot f of a equals g of f of a for all a that belongs to a. I repeat, its definition is g dot f of a equals g of f of a for each a that belongs to a. So one more thing, can you combine any functions? To combine two or more functions, or in general, when you're combining two functions, okay, the condition is that the codomain of one function, the codomain of one function should be the domain of the other function. I repeat, to form a composite function, okay, the codomain of one function should be the domain of other function. Now let us have a look at an example for. Here we have given three sets. One is set A with 4 elements, 1, 2, 3, 4. And set B with 3 elements, A, B, C. And set C with 4 elements, W, X, Y, and Z. We have given two functions f from a to b and g from b to c. In function f, as you can see on the slide, in function f, the element 1 of domain A is mapped to an element A of codomain B. Also, the element 2 of domain A is mapped to element A of codomain B. The element A of the element 3 of domain A is mapped to element B of codomain B. And the last element 4 of domain A is mapped to element C of codomain B. Similarly, in function g from B to C, the element A of domain B is mapped to element X of codomain C. The element B of domain B is mapped to element Y of codomain C. The element C of domain B is mapped to element Z of codomain C. In function, the codomain of function f is nothing but the domain of the function g. So now we can form the composite function from a to c, and that is denoted as g dot f. Okay, so g dot f is a function from a to c. So now the element the element 1 of A is mapped to element x of C. I mean, in function g dot f, the element 1 of domain A is mapped to element x of codomain C. Similarly, the element 2 of domain A is mapped to element x of codomain C. The element 3 of domain A is mapped to element y of codomain C. The element 4 of domain A is mapped to element z of codomain C. Got it? So this is will form a composite function. Now, in this slide, again, in this slide, I need to state that in general, composite functions need not be commutative. Okay, I mean, in this slide, I want to justify you that composite functions need not be commutative. Need not be commutative. See, for example, let f and g of functions from R to R. F and g of functions from R to R. So I can form, since the codomain of one function is nothing but domain of other function, we can add a composite functions, either f dot g or g dot f. I repeat, since codomain of one function is nothing but a domain of other function, we can have composite functions both f dot g and g dot f. But and one more thing, the definition of f is f of x equals x square. The definition of g is g of x equals x plus 5. Okay, so here I find g dot f of x equals x square plus 5, while f dot g of x is x square plus 10x plus 25. I mean, g dot f of x is not same as f dot g of x. So f dot g is not equal to g dot f. So in general, composite functions need not be commutative. So in this slide, I'm going to justify composite functions are always associative. Composite functions are always associative. Okay, here we are given three functions f, g, h, all three from R to R. The definition of f is f of x equals x square. The definition of g is g of x equals x plus 5. The definition of h is h of x equals square root of x square plus 2. So, the LHS of associative law, that is h dot g dot f, h dot g, the whole thing dot f, and h dot of g dot f are both equals to square root of x to the power 4 plus 10x square plus 27. So we will be justified here. Composite functions are always associative. Okay, clear? So Always remember, composite functions in general need not be commutative but always associative. Now, let us have a discussion about what is known as powers of functions. We usually compute 2 squared, 2 cubed, 2 to the power 4, 2 to the power 5, right? Similarly, if we are given a function f from a to a, we can define f to the power 1, f to the power 2, f to the power 3, f to the power 4, so and so on. Okay, such we call powers of functions. Now, let me tell you, if f is a function from a to a, we define f to the power 1 equals f, and for n belongs to z plus, f to the power n plus 1 is nothing but f dot f power n. I repeat, f to the power n plus 1 is nothing but f dot f to the power n. It's like recurrence relation. It's a recursive function. Okay. So I repeat, if f is a function from a to a, we define f to the power 1 equals f. It's an initial condition. And for n belongs to z plus, the recurrence relation is f to the power n plus 1 equals f dot f power n. Okay. So let us have a look at example 7. Here we are given one set A with 4 elements 1, 2, 3, 4. And we are given one function from A to A defined as f equals the first order pair 1, 2. It means 1 is mapped to 2. The second order pair 2, 2. 2 is mapped to 2. The third order pair 3, 1. It means 3 is mapped to 1. And the fourth order pair 4, 3. That is 4 is mapped to 3. So we are given function f. So we know how to apply composite functions, right? So the condition is that to form a composite function, the codomain of one function should be the domain of other function. So to compute f dot f, okay, the codomain and domain both are same, so we have a composite function. Okay, so what is f dot f? Okay, what are those per ordered pairs means? One is mapped to 2, 2 is mapped to 2, 3 is mapped to 2, 4 is mapped to 1. So let me tell you how we obtain this f dot f. Initially from f, okay, 1 is mapped to 2 and that 2 is mapped to 2. So 1 is mapped to 2. Next, 2 is mapped to 2. Again this 2 is mapped to 2. So we have 2 mapping to 2. Next, 3 is mapped to 1 and this 1 is mapped to 2. So we have 3 mapped to 2. Next, 4 is mapped to 3 and 3 is mapped to 1. So we have a mapping from 4 to 1. So this is how we are going to obtain f square. Now we have f square. So let me obtain f cube. So f cube is nothing but f dot f square. So from f square we have a mapping 1 to 2. and from F 2 is mapped to 2. So 1 is mapped to 2. Clear? So now in F square 2 is mapped to 2 and in F 2 is mapped to 2. So again 2 is mapped to 2. In F square 3 is mapped to 2 and in F2 is mapped to 2. So we have 3 mapped to 2 in F cube. In F square 4 is mapped to 1 and in F1 is mapped to 2. So in F cube we have 4 mapped to 2. So this is how we compute powers of functions. So this is about this session. Thank you for listening.